Okay, so let me start by reviewing briefly what we did last time. We asked the question, what possible transformation from one frame to another will preserve the speed of light? And I'll use names now, so I'll have a frame F and I'll have another frame F prime. Then the coordinates in this frame will be x and t, and the coordinates in this frame will be x prime and t prime. So if we are measuring something in one frame or another frame, don't take my drawings very seriously, then once we know the transformation between them, and the frame is moving, this one is moving with a velocity v. And for simplicity, we'll take that velocity to be in the x direction. Later we'll see what to do when there are more directions. Now the puzzle is that an experiment told us the speed of light is the same in frames f and f prime. That is the Michelson-Morley experiment. It didn't have to be so. It's a fact which can only be demonstrated by an experiment. Okay, so the origin of special theory of relativity did not happen by pure thought, like Einstein lying on his bed at night and imagining things. He actually took an experiment very seriously. Now that experiment basically measures the quantity c, which is equal to dx by dt, and compares it with the quantity c prime, which is equal to dx by dt prime. Of course, they didn't formalize it in this way, but this is just a way to say what they did. They measured this ratio, this dx by dt, which is nothing but the rate of change of position with time or velocity, in one frame, and found c as the answer. That was their goal. And then the same thing in another frame and found c prime as an answer. And then they want to compare c prime with c. Okay. So how many velocities are there in this problem? In principle, 3. C, c prime and v. If you're going to be mixed up about which one is c and which one is v, then you won't get very far. So it's very important to realize that these are formulae. Formulae cannot tell you the physics of the problem. The physics of the problem is, okay, I won't exactly tell you the physics of what these people did, but idealized version of physics of the problem is that they set up a Michelson-Morley experiment. I don't know how to draw it. Half silvered mirrors and all that blah blah here. And then this also, they go into a moving frame and they set it up here. Okay, that's how you can do the experiment in one frame and another frame. Now they didn't do that, they simply stayed on Earth, and Earth conveniently moved around the Sun, so that relative to whatever is the possible medium filling space, Earth would have been moving differently with respect to that medium at different times, so it's different frames. Okay, they could not get off the Earth and sit in the medium, interstellar medium, and do the experiment. They did it in 2 different frames, but they were moving with respect to each other because we were doing it at different times of the year. But you can always, since you're not going to repeat the experiment, you can always just imagine that there's one experiment on land at the docks, and another experiment on a ship also at the docks, and then the ship starts moving with velocity v. Now light is measured by the people on land. They find out c. The motion of light is measured by the people on the ship. They find out c prime, and they compare them, and they find the very surprising result that c is equal to c prime. And now our job is to understand what could be the relation between x prime, t prime, and x and t which maintains this. And we showed last time that a Galilean transformation, which only transforms x and not t, does not do this job. It simply cannot do this job, so it has to be wrong if the experiment is right. Continuing with that, we then asked for formulae relating x prime and t prime to x and t, and we asked for the formula to be linear because, okay, and what we want to do is to preserve this, but this equation is the same as minus c squared dt squared plus dx squared equals 0. So if I can preserve this quantity by change of frame, then I'm good. Then c is constant. So we allow for an arbitrary linear transformation. Many people asked why it's not a non-linear transformation. And actually, the moment we start doing general relativity, you will exactly see what happens if I try to make a nonlinear transformation. In a way, in fact, just think physically, a linear transformation means I go from a frame which is at rest, I just pick that arbitrarily, in which I don't feel any forces, and then I go onto a ship which is moving but at uniform velocity. Okay? If I would make a non-linear transformation, it would be something like moving at a non-uniform velocity. The ship might decide to go back and forth or speed up, slow down, do various things. Okay? And special relativity does not say that the laws of physics are unchanged if I get on a ship that is doing random things. Okay? But general relativity says that, and it's a much more subtle and difficult point to grasp. But we'll only come to that maybe on the 4th or 5th lecture of this course. So be patient. Till that time, we are doing linear transformations from one frame to another. Okay? And the linear transformation we found, which works perfectly, is this one. For any theta, this is the linear transformation. Then we said, well, it has to be connected to some physical quantity. The physical quantity can only be V, which is the only data I have which connects one frame to another frame. So how is theta related to V? And then we found that for small v, theta is approximately V by C, which is very good. Exactly what we want. However, this can't work for large v. Why did it even work for small v? Is because in small v, I ignore order v squared. So you have learnt in physics that when we take some parameter small, usually we call it epsilon, then it means that we are taking only terms of first order in epsilon and neglecting epsilon squared. So in that limit, this is good. And in that limit, we find that x prime is x minus vt. And we prefer to write this as this. And now what we do is, so this fits with this equation when sine hyperbolic theta is theta, which is for small theta, and theta is v by c. Then it satisfies this. This equation becomes equal to this equation. But in general, this equation is not equal to this equation, because in this one, cos squared minus sin squared is exactly 1 for all theta. And in this equation, coefficient of this squared minus coefficient of this squared is not exactly 1. It's 1 minus v squared by c squared. So we try to correct it in a way that will work for arbitrary theta and arbitrary v by just putting a gamma here and saying, well, that means that cos theta is actually equal to gamma and sinh of theta is v by c gamma. Did I do something wrong? Just can I do make mistakes all the time? Anything? Okay, good. So we try this, and now to satisfy this equation, which has to be true for any theta, including large, we simply allow ourselves to choose gamma. So it becomes gamma squared 1 minus v squared by c squared. This being 1 implies that gamma is 1 over square root of 1 minus v squared by c squared. So this is the stuff we did last time, and it has an enormous number of consequences. So let's look at the consequences today first. First of all, this transformation with gamma here and gamma given by this formula makes no sense if v is greater than c. Okay, so now v could be any velocity, right? It's just the velocity of some frame relative to another frame. But we have suddenly found that that velocity cannot cross c. That's not what we assumed. We only assumed light has the same velocity in both frames. But as an output, we found that v is always less than c. Certainly if it's greater than c, then this becomes negative, square root is imaginary, gamma is imaginary, coordinates become imaginary. That's a terrible thing. Coordinates have to be real. Okay. You might ask what happens if v is equal to c. Then also this change of frame becomes quite singular because this just diverges. This denominator becomes 0 and gamma becomes infinite. But since we have found that v is always less than c, let's work with the idea that v, the velocity of any material object other than light, is less than c, and it can approach c arbitrarily close, but it can't exactly become c or cross. These are true facts. Any of you who's taking quantum field theory will also learn the same facts in that course. Okay, all objects which possess a mass that's not 0 will move at a velocity v less than c. This I have not proved. This is what we know now with a mass. Move at v less than c. I proved that it has to be v less than or equal to c from that equation, but I couldn't rule out that an object with mass could move at velocity c, but in fact it can't. It is part of representation theory of Lorentz group, which is a bit of a fancy thing. You may study it at some point. On the other hand, v equals c, so all objects with mass exactly 0 move at this speed. So what about light? Well, it's made of photons. Photons have mass exactly 0, therefore light moves at the speed c, which is the same in all frames. Okay. What other objects do you know of which have exactly no mass? Gluons. It's tricky with gluons because formally they have no mass when you write down their equations, but in practice, because of strong nuclear force, they are confined, and that effectively makes them massive. So no, they don't move at the speed of light. Gravitational waves, excellent. So gravitational waves are real, but we don't know for sure that they are made of gravitons. So that particle wave duality which holds for light, we think it must hold for gravity waves also. If we are right, then gravity is carried by, the force of gravity is carried by gravitons, just like the light ray is made of photons. Okay, and if that is true, the graviton is indeed massless. And it's a general fact, which again you can learn in other courses, that a massless particle mediates long-range forces, and we know that the only long-range forces in the universe are gravity and electromagnetism, both of which obey Coulomb's law, 1 by r for the potential, 1 by r squared for the force. All other forces obey exponential to the minus r type of law. So they get damped off in a very short distance. So this is the picture that emerges. But saying all this, I've gone a little bit beyond what I can prove right now. But it's true. Good. Now, what more can we do? Well, we can take these two equations and divide them. So divide this by this, we get tan hyperbolic of theta is v by c. Exactly. Now it's not an approximation. That's very nice. So we've got an interpretation of theta, which is that tan hyperbolic of theta is v by c. This is exact. And even if you're not familiar with hyperbolic functions, just like tan of x is approximately x for small x, so also tan hyperbolic of x is approximately x for small x. So this equation agrees with what we knew earlier, that theta is roughly v by c, but this is an exact equation. Okay. Now some more fun consequences. Now we can do a very favorite trick, which is to have a frame f move with velocity v1, another frame f prime, and then a third frame f double prime moving at velocity v2 with respect to f prime. So we are composing them. How do I find out the Lorentz transformation between this and that frame? It should be possible. I think I mentioned this last time. So here I go from the port to the ship moving at velocity v1, and then on the ship for some reason there's a little toy train moving at velocity v2 along the ship, at least for some short time till it falls off. And now we want to know what is the rule to transform coordinates in f double prime into coordinates of f. Now naively you will say, well, in Galilean relativity we know the answer, because the transformation is x prime is x minus vt. So if I do it with v1 and v2, then I get v1 plus v2. But here there's this nonlinear factors 1 over square root of 1 minus v squared by c squared, which spoils everything. And so if we do the calculation, which is quite a simple one, before I even do that, this again confirms that v has to be less than c, because the tan hyperbolic function has this graph. This is theta, this is tan hyperbolic of theta, and this is 1, and this is minus 1. It simply goes from 1 to minus 1. How will you prove that? It's completely trivial. How will you prove it?
You can write it in the exponential form.
Very good. Always write it, thank you. Always write it in the exponential form. That's one function which is very easy to understand. So it's just e to the theta minus e to the minus theta. Upon e to the theta plus e to the minus theta. And now if theta goes to be large and positive, these terms are negligible and this ratio becomes 1. And if theta is large and negative, these terms become negligible and this ratio is 1, but there's a minus sign. And that proves what I've just drawn. So if tan is bounded between minus and plus 1, then of course so is v by c. V can always be negative because it just means the ship is moving backwards for some reason. But it can't go any faster than c this way or faster than c that way. So it's actually, if you include the possible sign of v, this is the limit, which is immediately imposed by this equation. So you see that we started by assuming something very, very simple, that the speed of light is the same in all frames, and all kind of things are coming out as a consequence. We don't have to keep adding assumptions. Okay, and now one more thing which comes out, which I've left for you as an exercise, is show that in this diagram, in this situation, f double prime is related to f by a Lorentz transformation. I'm going to call it a Lorentz boost. A boost is when we go from one frame to another frame that's moving. It will turn out that Lorentz transformation actually encompasses more general transformations, which are not all boosts. We'll come to that soon. So this, where v is equal to v1 plus v2 over 1 plus v1 v2 over c squared. In the signs, there can't be any. It's a beautiful and simple formula. You can actually play with it. I tried plotting the v against v1 and v2 in Mathematica. You get a very weird figure. You should try it. Okay. It has many weird properties. One is that if v2 is c, then independent of v1, v is also c. Okay. Another is if v1 and v2 are less than c, then v is less than c. A third one, which actually I didn't even realize, if v1 and v2 are greater than c, both of them, which is unphysical, still v is less than c. It's a very strange formula. Try it. It has all kinds of things, but what it does is it always makes sure that if v1 and v2 are less than c, this formula implies that v is less than c. So by repeatedly boosting and going to different frames, I'm never going to cross the velocity of it. It's a great result. Okay. Now another surprise, a very nice one. Supposing I ask this question, well, the frame can be defined by the velocity v, which is the physical observable, or by the mathematical parameter theta, which I told you it has a name. It's called rapidity. Okay. So theta, v, we saw that it adds like this. This is the addition theorem for velocities, and it's not the simple one. What happens to theta? How does theta compose? Like if I do a boost with parameter theta 1 and theta 2, what will be theta of the composed term? And the answer is very nice. In terms of theta, the theta of this frame relative to this frame is just theta 1 plus theta 2. It's additive. This is why the parameter is so nice in special relativity. You just have to keep adding it. So every time you do a boost, you just add the theta of that boost and you're done. This is the same formula as this under the relation that tan hyperbolic of theta is V by C. It's an exercise. Okay, so theta is added. So rapidity is added. So there's no limit on rapidity. A frame can have a rapidity, any theta between minus and plus infinity, but the speed of light is not theta. It is the number that you get by inverting tan hyperbolic of theta, and that number is bounded by 1. Good. Are there any questions? If not, we'll move on to some new things. Did everybody know all this? I mean, I'll be very happy if you knew all this really well. But I also will be happy if you felt it was useful. We'll keep on doing simple things, but I promise you they will get more complicated very fast. So if you find the first 2-3 lectures too simple, don't worry, it'll change. Good. So now we'll drop mathematics for a little while and go back to physics. But actually we won't go back to physics, we'll go to geometry. So what we'll do is learn a new way of studying physics, physical events, which was not commonly used before the advent of special relativity, and that is called the space-time diagram. Much of the time when you see two axes, they are y and x. In fact, the standard labeling of two axes is x and y. And x and y we think of as positions in a plane, coordinates in a plane, and then if there's a third direction we want to include, then we call it z and we draw it. So we draw something like x here, y here, and z upwards. And we do all our physics that way. Or sometimes we plot, for example, x here and time here because we are looking for the time evolution of something. For example, your sine wave is plotted with x there and t here. Okay. Here we are going to think of all physical events as being drawn with x and y in a plane. Z is too difficult to include, so we are never going to include it. And CT in the vertical axis, because CT has dimension of length. So all these can have the same scale. Okay. Now we need to think what are very common things in our life on this diagram. And the first, it's not a great surprise, but it's worth realizing. The first point is that supposing I start here, this is me and I'm fast asleep, I'm not going anywhere. Okay, how am I supposed to represent me? Is me the same as this point? No, it's this point at time t equals 0, and me for the rest of time, as long as I remain in bed, is this line. So a stationary object still has a line describing it. Okay, and this line, and any other object will have another line describing it. We can have very simple lines, we can have very jagged lines. Every object will be described by a line in space-time, and what that line means is what is the position of the object at a given time t. Now there are certain constraints on this line. For example, I can't have a line which gives me, I can't have a line like this. Okay, why is that? This is me. After some time I'm reaching here and I'm at this point x. Let's ignore y for now. And now I suddenly seem to go backward in time. I can't do that. We don't go backward in time. So such things are wrong. And in fact, what I can do is, if this line was possible, I would draw a dotted line here and notice that I'm at three different places at the same time. That can't happen. I can be at the same place at 3 different times, but I can't be at the same time in 3 different places. Simple fact of life. So this is not allowed. Okay. What else is not allowed? Well, let me draw this line at 45 degrees. This is the line x equals ct, because this is x and that is ct. So light travels on this line, always. That's what the experiment we discussed tells us, that light always travels on that line. Of course, light doesn't have to travel in this direction. It could travel in this direction at 45 degrees. It would simply be going along minus x-axis at the same speed. And actually even that's not necessary. Now let's put back the y coordinate. So this pair of lines turns into a cone like that. And light can travel anywhere along that cone, but always along the cone. And this cone goes by the very simple name of light cone. Now what about me? These are all the world lines I drew for myself, and as the world line of myself gets here, very close to this 45-degree line, I am moving at a speed close to the speed of light, which is theoretically possible. Okay, but from what I told you earlier, my world line will never tip over and reach the speed of light. Okay, now I'm just telling you a lot of words and I'm not writing down these words, and they are not even written in the notes. You have to sort of understand what I'm telling you and then read about it or work it out yourselves. It's very important. And do all kind of weird thought experiments like what if this and what if that. I'll give you one weird example. Supposing this was me sleeping in my bed, and I suddenly got up, went somewhere, maybe the bathroom, and I came back and I went back to sleep. Perfectly fair, except that this would not be jagged, it would be smooth, but yeah, that's perfectly fair. In principle, I could have gone to the bathroom at the speed of light or close to the speed of light and come back also at speed of light, or I could have come back much slower, or I could have, because I was done with my job, so now I can come back slowly like that. Okay, but what can I not do? I can't get up from my sleep and go to the bathroom like this, because to do that I have to go faster than light. So this path, even though it never crosses this one, and my average speed over time is much less than the speed of light. In fact, my average speed is 0 because finally I'm back in bed. Okay, but for a short time I moved at a speed faster than light, not allowed. So you see, there's a very restrictive rule about what paths I can follow. That's very important to realize. So let me write at least 2 rules. Can't go, I think there's basically one rule. There are 2 rules. Can't go forward and backward in time. Two, can't move faster than c, even for a very small piece. Okay, but for example, what I can do in principle, again not violating any laws of physics, would be to travel at the speed of light for some time, travel back, travel again out at the speed of light, travel back. I can do this. This is allowed. Just about near the speed of light, yes.
But you can go forward in time, right? You cannot go backward in time.
Yes, exactly.
You said can't go forward and backward.
Sorry, I just wrote something stupid. Thank you so much. That's what I wanted to write. Yes, exactly what I wanted to write. I often write things different from what I'm thinking, but okay, this is what I meant to say. Can't go backward in time, can't move faster than c. Okay, let's say that this curve is highly tilted, very approximately close to c, but is less than c. Then what I've done is, from my bed, I've suddenly gone off that way at the speed of light for a few seconds, then stopped and came back. This point represents where I stopped. And I reversed my speed because my direction was that way, now it's that way. My direction changed. Time, of course, never reverses. So the way I'm going along x here was increasing and here it's decreasing, and I'm back to where I started. This I can keep doing. These are allowed trajectories. Okay. So, and these, all these paths, whatever are the allowed paths, go by the name of world line. And there's a bit of confusion in the terminology because we often call them paths. But a path, usually in pre-relativistic physics, just means the actual path I walk. Like the garden path is not a space-time path, it's just a path in space. From here to the main building, you go along this curved thing with bushes in the middle. That is just a path. But space-time paths are called world line, and we often will call them path anyway. So you need to figure out, is it a space-time path or a spatial path? That you need to at all times think, because it's not always going to be told. We also use the word trajectory, path or trajectory. So my only warning is that these words are older than relativity, and they actually have a well-defined meaning, which is not space-time meaning, which is a spatial meaning. This is the new phrase that was invented to fit relativity, but we equivalently use this. Okay, good. Okay, now you may ask the following question. Supposing I take this space-time diagram and draw a straight line path. One more point to note is that a straight line path means motion at constant speed. Anything else will not be straight. Okay? Because obviously the position is increasing linearly with time. As I keep telling you, don't take my diagrams too seriously. Straight paths are also not straight, but anyway. So this is the path. Now the question is, given this path, what is v? Every straight line path has a v, the velocity, but what is it actually given the geometry of this path? Okay. Now you can see that if this is the angle alpha, again I am doing something different from what people normally do. Normally the angle alpha is taken on this side of any line and then we get the slope, but I want to take the angle alpha that way. Then tan of alpha is nothing but x traveled on that path divided by the time in units of c taken, so it's x upon ct. Okay, and this is nothing but our old friend v by c, but this is tan of alpha, this is not tan hyperbolic. Okay, so tan of alpha is v by c, gives me the actual angle which I can convert into velocity, namely for any angle that I find that my path makes with the vertical, tan of that angle will be v by c, and tan has the property that it goes between -1 and +1 for angles between -45 and +45, not over the whole range. So minus pi by 4 less than alpha less than pi by 4 implies -1 less than tan alpha less than 1, and so we are back to our old friend v by c being less than 1, which it has to be. Okay, and in fact we get the relation that tan alpha is tan hyperbolic theta, but theta can have any range from minus to plus infinity. Alpha has only a range minus pi by 4 to plus pi by 4. So the advantage of this parameter is that it's geometric. We can see it on a space-time diagram because it tells me an angle. Okay, this parameter is physical because it tells me a velocity, and this parameter is neither actually. It's the most mathematically natural parameter, but all three you can go from any one to the other, so all are good. I've left it as an exercise to ask what is the composition law of alphas. You see, theta is additive and v adds like this. What is the composition law if I have one angle alpha and then I go in a boosted frame by another angle? Every frame is parameterized by an angle alpha in that language, just by this formula. Then what is the combination of two alphas? What's the formula? You can work it out. Good. Okay, any questions? Otherwise we'll move on to something else. Oh, one thing I forgot to say was that in a space-time diagram, if I just look at a dot, a point, it's called an event, because the dot comes with a position and a time. Okay, So a dot is a space-time event. A space-time point is an event, and a world line is actually an object. And that's what you need to remember. Good. Okay. Now all this is very nice. We've done some geometric construction and some algebra, but we need to formalize it so that we can actually have some precise formulae for special relativity, and then we'll generalize those formulae to get general relativity. Now, in this story, a very important role is played by rotations. We haven't mentioned rotations at all. Interesting fact, rotations also preserve the speed of light. We never asked for all transformations that preserve the speed of light, but rotations do that. Okay, that also our friends Michelson and Morley could have done by simply turning their apparatus. They would see that rotations preserve the speed of light. And why is that? Because the full expression that's preserved, usually we are lazy and we just write some one dimension x, but if we put all the dimensions, rotations will be a linear combination between x and y, or y and z, or x and z. But boosts will be a linear combination between t and x, t and y, or t and z. So there are three rotations. In physics, we often label rotations by an axis around which the rotation is done, but giving an axis is the same as giving a plane orthogonal to that axis, and actually it's better to use the plane to specify the rotation. Because the xy rotation means that I'm changing x and y both such that dx squared plus dy squared is fixed, and you know the answer for that. This rotation is just cos phi minus sin phi cos phi. So x prime y prime is this times x. You see how similar it is to the Lorentz transformation, but different. It's different in an important way. These are cos and sine, not cos and sinh. Why is that important? Because I can't make a rotation which is too big, because after phi becomes 2 pi, I'm back where I started. In physics we say, or in mathematics we say, this is a compact direction. Compact means something which is angle valued. So after some finite amount, it comes back to itself. It doesn't stop. It's not like there's a maximum phi. You can take phi as large as you like, but the function keeps repeating. So it's periodic. So phi is angle valued. That's not true of the theta, which occurs in Lorentz boosts. It's not angle valued, and that's good because, as we see, we can take any theta however large we like. Okay, but the mathematics is not that different between mixing x and y and mixing x and t. Except for one thing, t comes with a minus sign, and all the space positions come with space coordinates come with a plus sign. So the mathematics is actually finally different. Okay, but there are important similarities, and one of the most important facts is that the most general transformation which preserves this whole thing is an arbitrary combination of any rotation and any boost. We only did a one-dimensional version of boosts, but the most general is the one which is any rotation, any boost. You can just keep composing them. Do a rotation, then do a boost, another rotation, different axis, boost in different direction, whatever you like. The final result will be specified by 6 parameters. One parameter for every rotation in 3 planes, and one boost for every direction of boost x, y, or z. Is that clear?
Sir, I have a
Yes, please.
if we have two stationary frames, spatially stationary,
Yes.
and one of them is rotating very fast.
No, it's not rotating. I rotate the frame. That means I compare a frame and another frame. I don't rotate. Don't think of rotation as something which is spinning. A frame and a rotated frame. It's not a process. Just like when I have the ship moving at velocity v, I don't discuss the phase when the ship starts and goes from velocity 0 to v. Okay? I just have one frame and another frame, and I do the experiment in both. In this case, I have one frame, which is my bench in my lab, and my other frame is the same bench after some students have picked it up and rotated it for me by the angle phi. That's all. If you have really seen an optical bench, this is not possible because nobody can lift it. I don't know if you have seen the optical benches here, they're incredibly heavy. But in principle, that's how we rotate frames. So it's not a spinning frame. That's a completely different thing. Actually, the spinning frame, if you realize, it has a velocity, and the velocity is also different everywhere because points further from the axis of rotation are moving faster. So it's neither the frame of a ship nor it's the frame of a rotated frame. It's something totally different. And as you're probably guessing, that induces an acceleration, and that's the subject of general relativity and not special relativity. So this is everything we can do to just preserve the speed of light by a linear transformation. 3 rotations and 3 boosts. And in fact, if you're interested, so let's put the boosts here. Tx, Ty, Tz. The fact that T is there is built into the definition of boost, because boost means I somehow mix time with one space direction, which is the effect of a velocity. Okay. Now let's review very quickly what we know about rotations. Question? So, under rotations, all physical quantities have some definite property. And let me list a few of the examples. So, one is we have a scalar quantity. So, this satisfies sorry, I'm using phi again. Now it's not an angle, it's the name of the quantity. Phi of x prime, phi prime of x prime is equal to phi of x. This means that it does not transform under a rotation, namely after I rotate, I get the same system, but it's very important to note that there's a prime on both of these. Why? Because phi of x is a function, okay? It evaluates to be the value of that quantity at that point. Now, if that point has a different coordinate x prime after I rotated my frame, then the function needs to change so that this, when evaluated at the same point, gives me the same answer. Yes, I'm explaining why there's a prime here and a prime here. Phi is a function of x. I'll give you an example in a few seconds. Phi is a function of x, so if I know the x coordinate of a point, then when I evaluate the function phi at that x value, I'll get the value of phi. That's a physically measurable quantity. Okay? I'm assuming, and I'll give you examples. Now the same point has a different value of its coordinate in a rotated or boosted frame. Okay, now I'm not considering boost, right now I'm just considering rotations. So since this x prime is a different number from x, though it's representing the same point, so phi prime has to be a different function of its own argument compared with phi, so that when I evaluate it on this new coordinate, I get back the same answer for the same physical observable. To give you an example, let phi be the temperature at a point on Earth. Okay? So temperature, let's say that for some reason I work out what is the function. I take some line across the Earth and I work out the function t of x on that line at a particular time. I'll do everything at a fixed time. Okay, so I just look up all the weather readings. This is the temperature at here, and then going west and going east from Pune until I cover some long part of some long line on the globe. Now to specify x, I have to give you the latitude and longitude. Okay, now if I rotate my latitude and longitude axis, that's a rotated frame. Okay, I'll just do it locally. I'll tilt them. Now the value of the x prime, which is both of these are vectors, 2 component vectors since I'm on the surface of the Earth. So the value of the components of x prime are different from x. They are the rotated values given by exactly this expression. Okay, so phi prime cannot be the same function as phi, because what its job is that when evaluated at this number, which corresponds to the same point where I started, it should give me the same temperature. So it's the evaluation at the point which is equal to the evaluation at the point. That's why there's a prime on both, there's no prime on both. That's the way to think of it. There's also, if you really want to confuse yourself, there are endless pages in textbooks on active and passive transformations. I never could understand any of it, and so I'm not recommending that you try. Once you know this, all formulae that we'll use will follow. Was the point clear though? The important central feature is that neither x nor x prime is really the point. The point is a place. The point could be this place where I'm standing. The place exists independent whether I call it x or x prime. Those are just labels which I find by measuring something. Point is there. So if the temperature at that point is well defined, then it can be described by two different functions depending on choice of two different coordinates. The same thing will operate when we look at boosts also, but we'll come to those later. So this is a scalar. Temperature is a classic example of a scalar, but for example, density of a fluid is also a scalar. So temperature is an example, density is an example, and here you just need to know physics, right? Density of a fluid is something at some point. I take a little tiny infinitesimal cube and I calculate the mass and the volume and I divide one by the other, I get an answer. How does it matter whether that thing is being looked at from this side or that side? It shouldn't matter. The density is measurable. So it's a scale. Then we have vectors. And there are many examples. So there's velocity, acceleration, force, vector potential, electric field, magnetic field. These are a few of the examples in physics. I hope you know all of them. Here I'll also put scalar potential of electromagnetism. That's actually called phi and it's a scalar under rotations. Okay, I hope you know all these symbols. I don't have to explain everything. Well, how do they transform? Well, we know that under a rotation, the coordinates, now I'll introduce I for the components. This is nothing but x, y, and z. So xi prime is some matrix Oij times xj. Is the matrix which I erased, that cos theta minus sin theta thing. Okay. So this defines a rotation. So actually I can add x also here. X itself is a vector, and then everything else is also a vector just like x. Okay. What is the key property of rotation? It preserves the length of the vector. So xi prime should be equal to xi, where I sum on both sides, I going from 1 to 3. Most often I am not going to write this summation, so we will use what is called Einstein summation convention. Have you used it before? Okay. So that whenever they are repeated indices, we sum over their allowed range. And from this, we get the equation, this is quite important, that Oij Oik is equal to delta Jk. Now, when I have an index object with two indices, it's just a matrix. It's a 3 by 3 matrix, and this product Oij Oik is not a matrix product. Matrix product is always done by writing one index, next index, then this index same as this one, and then last one is different, and then I sum over the common index. So to make this a matrix product, I can transpose O and write this as O transpose Ji. So Oij is same as O transpose Ji. Here I have Oik, this is delta Jk, and now I can just write it abstractly as O transpose O is equal to 1. Identity matrix, and this tells me that rotations are given by orthogonal matrices, which we all know. Okay. Now what about these physical quantities? Okay, before I say that, let's also write this equation in one form which will be useful, if not today then tomorrow. We can also write this equation as O transpose 1 O equals 1. I just put a 1 in between, it's quite harmless. This gives me the interpretation that an orthogonal transformation is the transformation which preserves the identity matrix. It acts by, the operation acts by O on the right and its transpose on the left. That's called as some kind of similarity transformation, and it preserves the identity. So that's one way to look at it. Good. Now we immediately know how V transforms. It must be that if I have a velocity in one frame and I measure it in a rotated frame, the same matrix O transforms the velocity and the acceleration and all of these. Just saying that there are three vectors tells me what they do under a rotation without any extra work. I find out what is the O matrix for my rotation, and then I can blindly apply it on all three vector quantities, and I'll find the new one from the old one. Good, right? So this is why we focus so much on whether something is a scalar or a vector. It's because after changing frame by a rotation, we know immediately what they are going to be. We don't have to go back and worry about what did they change to. This is the rule, and it's the same rule for everybody, for vectors. Now there's one more level of complication, and this is called tensors. It scares everybody, but there's nothing to be scared of here. The best way is to actually give an example. So suppose I have a velocity in a fluid. Now in a fluid, in each point of the fluid will have some velocity, but it can vary as I go sideways, perpendicular to the fluid flow. And it can also vary as I go forward and back. So I have a velocity field. So you can imagine the fluid here, and everywhere there's a velocity vector. But it keeps, oh, this is very bad. No notation for it. I can't put an arrow on an arrow. Okay, well, so this is, okay, you can just think this is V1, this is V2, this is V3. Each point has some continuously varying velocity. Okay. So I might want to study the gradient of the velocity, which in components is best written like this. Now sometimes books will say this is dyadic something something, lot of words. It's just an object with two indices because I started with a vector and I'm asking for its change in a direction. One index tells me which component of the vector, the other index tells me in which direction I'm looking at the change. It's not very difficult. Okay. And often people symmetrize it, so they consider separately this combination and another combination with minus sign, and this one is called the strain or shear tensor, and it's given the name Lij. It has two indices because of what I just told you, and my question is how will it transform under rotation? So what's the answer to that? Utterly simple. You have to think of each index as an entity which transforms under rotation. So just act with an O on one index and O on the other index and you're done. So L prime Ij of x prime is Oik Ojl Lk L of x. Was that difficult? It's as if I first focused on the first index and I said I should become K with an O acting on it, and then J should become L with an O acting on it. Once you have seen this formula, you can write down the transformation law for an arbitrary tensor which has any number of indices, one O for every index. That simple. The point here is that there are physical quantities like the strain tensor which are not vectors and not scalars, they are tensors. So if you wrongly assume they are vectors or scalars, you will not work out the correct transformation law under a rotation. This is the transformation law. You need to at least know that fact. Is it clear? Have you seen this formula before? It's a very simple formula. Okay, some of you have seen it, I think. Okay. Now, it's very important that these things are true because otherwise, lots of equations of physics would just go to hell. For example, we have an equation like del, okay, let's take first a simpler equation, E equals minus gradient phi. Electrostatics. So if I write it in index notation, which I favor, this is me now, I know it. 2 minutes and we are done. I hope it's clear the relation between this and this. It's the same thing, exactly same. So if I write this, it can only make sense because this is a vector and this is a vector. I can't have any equation where the left side is a vector and the right side is a tensor. If two things are equal, they must be both scalars or both vectors or both tensors. Okay? Also, from another equation which you know, del dot E equals 4 pi rho, this is a scalar, but this is a vector and this is a vector. So we also learn that the vectorness of two quantities, when I use the dot product, it cancels out. Though this changes under rotation and this also changes under rotation, but this combination doesn't change under rotation. Okay, and that's because of the orthogonal nature of O. This will change by an O, this will change by another O, but O transpose O is 1, and so the dot product doesn't change. So these are very important in making the laws of physics. Like you can't make a law of physics which says that this is equal to a current. You would have never seen an equation like this in Maxwell's equation because it can't happen. It's not an experimental question. It's a simple statement of rotational invariance of physics. This is not possible. So now we'll generalize all these ideas to Lorentz transformations. And I hope that this discussion, though it was very elementary, will simplify what we are supposed to do tomorrow. So we'll meet tomorrow at 12 in the usual room upstairs.